Alright, let's continue. Let me open the table of content first. Okay. Previously we are on chapter 18 and now we are on chapter 19. Paging faster translation here. Let me open that. Wait a minute. Okay. Alright. We are in this chapter now, paging faster translation. Okay. Using paging as the core mechanism to support virtual memory can lead to high performance overhead. By chopping the address space into small fixed size unit, that is pages, paging requires a large amount of mapping information, right? Because that mapping information is generally stored in physical memory. Paging logically requires an extra memory lookup for each virtual address generated by the program, going to memory for translation information before free instruction fetch or explicit load or store is prohibitively slow. Going to memory for translation information before every instruction fetch or explicit load or store is prohibitively slow, and thus our problem, the crux, how to speed up address translation. How can we speed up address translation and generally avoid the extra memory reference that paging seems to require? What hardware support is required? What operating system involvement is needed? When we want to make things fast, the operating system usually needs some help, and help often comes from the operating system old friend, the hardware. To speed address translation, we are going to add what is called, for historical reason, a translation look aside buffer, or TLB. A TLB is part of the chip's memory management unit and is simply a hardware case of popular virtual to physical address translation. Thus, a better name would be an address translation case upon its virtual memory reference. The hardware first checks the TLB to see if the desired translation is held therein. If so, the translation is performed quickly without having to consult the page table, which has all translation. Because of their tremendous performance impact, TLB or translation look aside buffer in a real sense make virtual memory possible. Okay, this is TLB control flow algorithm. I think PTA in here means page table entry, but what is PTPR? PTA but what is PTPR? Page table base what? I'm assuming P is the base, but what is the R? Right, page table entry address. And this one I assume is the what is it called? The offset, maybe something like that. Yeah, I'm still not sure about PTPR here. Okay, and then we access the memory from the page table entry address here. If the page table entry valid or not valid in this case, in this conditional, we raise exception segmentation fault. If we don't have the permission from the protection bits here, we got an exception protection fault. And if everything fine, then yeah, we insert the current translation to the translation look aside buffer, something like that. Maybe, yeah, I'm still not sure about this PTRPR. Okay, let me continue this. TLP basic algorithm, the translation look aside buffer basic algorithm. Figure 19.1 shows a rough sketch of how hardware might handle a virtual trace translation, assuming a simple linear page table. That is, the page table is an array and a hardware manages TLP, translation look aside buffer. That is, the hardware handles much of the responsibility of page table access. We'll explain more about this below. Okay, how hardware might handle a virtual address translation, and a hardware manages TLP. Okay. The algorithm the hardware follows like this. First, extract the virtual page number from the virtual address, right? And one in figure 19.1, this one, right? We are using the masking to only get the virtual page number bits, the binary digit, and then right shift to, what is it called, to remove the unused bit, something like that. and then we get the virtual page number or the index. And check if the translation look aside buffer holds the translation for this virtual page number in line 2. This one. Okay. If it does, we have a TLB hit or translation look aside buffer hit, which means the translation look aside buffer hold the translation success. We can now extract the page frame number from the relevant translation look aside buffer entry. Concat that onto the offset from the original virtual address and from the desired physical address and access memory and 5 until 7. I think this one, right? Okay. Assuming protection check do not fail on line 4. This one. Yeah, if we have permission, then we can access the memory. If we didn't have the permission, we will get an exception protection fault. Okay. If the CPU does not find the translation in the translation look aside buffer or a TLB miss, we have some more work to do. In this example, the hardware access the page table to find the translation and 11 until 12. This one. Yeah, I'm kind of curious what PTBR stands for. Line 11 until 12, and assuming that the virtual memory reference generated by the process is valid and accessible, line 13 and 15, this one and this one, right? Update the translation look aside buffer with the translation line 18. I think this one. Assuming that generated by the process is valid and accessible, right? If it is not valid, we got exception segmentation fault, and if we don't have the permission, we get the protection fault. Okay. Alright. This set of action are costly, primarily because of the extra memory reference needed to access the page table line 12. Okay. Finally, once the TLB or the translation look aside buffer is updated, the hardware retrieves the instruction. This time the translation is found in the translation look aside buffer and the memory reference is processed quickly. The translation look aside buffer, like our case, is built on the premise that in the common case, translations are found in the case that is are hits is put on the premise that in the common case, translations are found in the case that is are hits. If so, this is the TLP hits, right? Something like that. If so, little overhead is added as the translation look aside buffer is found near the processing core and is designed to be quite fast. When a miss occurs, the high cost of patching is occur. The page table must be accessed to find the translation, okay, and an extra memory reference or more with more complex page table result. If this happens often, the program will likely run noticeably more slowly. Memory access relative to most CPU instructions are quite costly, and translation look aside buffer mislead to more memory access. Mislead to more memory access. Noticeably more slowly. Memory access relative to most CPU instructions are quite costly. TLP miss lead to more memory access. Thus, it is our hope to avoid TLP miss as much as we can. And I'm kind of curious too. What happens if the data, if the translation, what is it called? Translation address is out of date. Is there any case when the translation address in TLP or translation look aside buffer out of date? Like any case, right? Case can also be out of date and we need to update the case, the data in the case, something like that. Okay, maybe we will find that out later on. We will see. Okay, example, accessing an array. To make clear the operation of a TLP, let's examine a simple virtual address trace. And see how a TLP can improve its performance. In this example, let's assume we have an array of 10 4-byte integers in memory. To make clear the operation of a TLP, let's examine a simple virtual address trace and see how a TLP can improve its performance. In this example, let's assume we have an array of 10 with 4-byte integers in memory. starting at virtual address 100. Oh, okay. Assume further that we have a small 8-bit virtual address space. A small 8-bit virtual address space. Okay, with 16-byte page. Thus, virtual address breaks down into a 4-bit virtual page number. There are 16 virtual pages. Wait. Okay. 8-bit virtual address space. Okay, something like this. With 16-byte pages. So I'm assuming this is the, what is it called? The page size, I guess. Maybe something like that. Okay. Yeah. Algorithm 14. Okay. Six. Is this correct? I'm not sure. 4-bit virtual page number and a 4-bit offset. Oh. Okay. 16-byte page. There are 16 virtual pages. Okay, and then there are 16 bytes on each of those pages. 16 bytes on each of those pages. Wait. Oh, okay. Right. This one is 16K. Okay, my bad. Yeah, okay, something like this. And then we have this, right? Okay, so something like this. Alright. So we have 4-bit virtual page number and another 4-bit for offset. Okay, here. Figure 19.2 on page 4 shows the array laid out on the 16-byte page of the system. As you can see, the array's first entry, this one, begins on virtual page number 06 with offset 04. Only 3 4-byte integer fit onto that page. 3 4-byte integer fit onto that page. Why is it only 3? The array continues onto the next page where the next 4 entries are found. Wait a minute. Let me try this. Begins on. Begins on. Okay. This is the virtual page number. This is the offset. Okay. So I'm assuming. What is it called? Virtual page number 00. Wait. No. It start on virtual test 100. The array first entry. Array first entry. Then like this. Offset 04. Three 4-byte integer fit onto that page. Yeah, I'm curious. How do we cut this information? Is it from this one? Virtual page number and then the offset. The array continues onto the next page. For bit offset. Is it from the 4-bit offset here? I mean, let's say something like this, maybe. The combination of the bit, maybe something like that. But is it? I'm not sure. Only 3 4-bit integer fit. Okay. This is the start. We have the, what is it called? The 16-byte for one page. So yeah, maybe something like this. 1 2 3 4 5. 1 2 3 4 5. Okay, right, this is the from the offset bit possibility, maybe something like this. And Yeah, because we assume we start from the offset 4, right? Not from offset 0. So only 3 4-byte integer fit. Okay. But the whole page one, two, three, 4. But the whole page should fit for 4-byte integer if we start from offset 0. Okay. The array continues onto the next page where the next 4 entries are found. Okay. Finally, the last 3 entries of the 10 entry array are located on the next page of the address space, virtual page number 08. Now let's consider a simple loop that accesses each array element, something that would look like this in C. Okay. Alright. Less than 10. Okay. Oh, okay. Assuming causality value in the array. For the sake of simplicity, we will pretend that the only memory access the loop generates are to the array. We will pretend that the only memory access the loop generate are the array, ignoring the variables I and sum, as well as the instructions themselves. When the first array element A0 is accessed, the CPU will see a load to virtual address 100. The hardware extract the virtual page number from this, okay, and use that to check the translation look aside buffer for a valid translation. Assuming this is the first time the program access the array, the result will be a TLB miss. Assuming this is the first time the program access the array, the result will be a TLB miss. The next access to array index 1, and there is some good news here. A translation look aside buffer hit. Oh, because the second element of the array is back next to the first. It lives on the same page because we've already accessed this page when accessing the first element of the array. Okay. Live on the same page because we have already accessed this page when accessing the first element of the array. Accessing the first element of the array. The translation is already loaded into the translation look aside buffer, right? Already load into the translation look aside buffer, and hence the reason for our success. Access to array index 2 encounter similar success, another hit, because it live on the same page as array index 0 and array index 1. Figure 19.2 example, an array in a tiny address space. Okay. Unfortunately, when the program access array index 3, we encounter another TLP miss. However, once again, the next entries array index 4 until array index 6 will hit in the TLP, the transaction look aside buffer, as they all reside on the same page in memory. Finally, access to array index 7 cause one last TLP miss. The hardware once again consult the page table to figure out the location of this virtual page in physical memory and updates the TLP accordingly, the translation look aside buffer accordingly. The final two access array index X and array index 9 receive the benefit of this TLP update when the hardware look in the take a look at the translation look aside buffer for their translation. Two more hits result. And the hardware look in the translation look aside buffer for the translation, two more hit result. Let us summarize the translation look aside buffer activity. During our 10 access to the array, miss and then hit, miss and then hit again until the end of the page, and then starting on the new page, miss and then hit again. Thus our transaction look aside buffer hit rate, which is the number of hits divided by the total number of access, is 70%. Although this is not too high, indeed, with desired hit rates that approach 100%, it is non-zero, which may be a surprise, even though this is the first time the program accessed the array. The translation look aside buffer improve performance due to spatial locality. The elements of the array are packed tightly into bits. That is, they are close to one another in space, and thus only the first access to an element on a page is a translation aside buffer miss. That make me curious. What is it called? If we putting the, what is it called? This, the array, what is it called? If we put every program memory translation into translation look asset buffer, isn't the TLP gonna be full? How do I replace that? If I put the memory transmission in TLP, isn't the TLP gonna be full at some point? Or maybe there is some kind of, what is it called? The cleanup mechanism in the TLP. Some kind of cleanup mechanism to remove the unused memory transmission. Maybe something like this. Yeah, the point is maybe this one, the cleanup mechanism to remove unused memory transmission in TLP. Okay. The element of the array are packed tightly into bits, that is, they are close to one another in space, and thus only the first access to an element on a page yield TLP mesh. Also note the role that page size plays in this example. If the page size had simply been twice as big, 32 bytes, not 16, the array access would suffer even fewer misses. Okay. As typical page size are more like 4 kilobytes, this type of dense array-based access achieves excellent TLP performance, encountering only a single miss per page of access. One last point, let me continue read this before reading the tip. One last point about TLP performance. If the program soon after this loop completes access the array again, we would likely see an even better result. Oh, soon after this loop completes access the array again, we would likely see an even better result, assuming that we have a big enough TLP. See, big enough TLP or translation look asset buffer to guess the needed translation. Everything hit. Right. In this case, the translation look asset buffer hit rate would be high because of temporal locality. That is the quick re-referencing of memory items in time. Like any case, translation look asset buffer rely upon both spatial and temporal locality for success. I am still not sure about this one. I mean, I've read this from somewhere else, but Yeah, I'm still not familiar with spatial and temporal locality. The translation look aside buffer rely upon both spatial and temporal locality for success, which are program properties. If the program of interest exhibits such locality, and many programs do, the translation look aside buffer hit rate will likely be high. Let me put this in here. What is spatial locality and then temporal locality? Okay, let me read the tip. Use caching when possible. Okay, caching is one of the most fundamental performance technique in computer system, one that is used again and again to make the common cache phase. The idea behind hardware cache is to take advantage of locality in instruction and data reference. Behind hardware cache is to take advantage of locality in instruction and data reference. There are usually two types of locality: temporal locality and spatial locality. With temporal locality, the idea is that an instruction or data item that has been recently accessed will likely be reaccessed soon in the future. Oh. Locality how to explain this? Means that an instruction or data item think of a loop variable or instruction in a loop. They are accessed repeatedly over time. Okay. Means that an instruction or data item that recently accessed has been recently accessed will likely be reaccessed later on in the future. Yeah, maybe something like this. Will likely be reaccessed later on. Think of loop variable or instruction in a loop. Yeah, let me take notes of this. Think of loop variable or instruction in a loop. They are accessed repeatedly. Okay, over time. With spatial locality, the idea is that if a program accesses memory at address X, it will likely soon access memory near X. Oh, okay. Means that if a program access memory at address, let's say N, the program will likely access memory near address N later on. Okay. Imagine here streaming through an array of some sort. Think of accessing. Imagine here streaming through an array of some kind, accessing one element and then the next one. See an array. After accessing one element, we might access the next element too. Okay, accessing one element and then the next. Of course, these properties depend on the exact nature of the program, and those are not hard and fast now, but more like rules of thumb. Hardware case, whether for instruction, data, or text translation, as in our translation look aside buffer, take advantage of locality by keeping copies of memory in small phase on chip memory. Take advantage of locality by keeping copies of memory in small phase on chip memory, instead of having to go to a slow memory to satisfy a request. The processor can first check if a nearby copy exists in a cache. If it does, the processor can access it quickly, that is in a few CPU cycles, and avoid spending the costly time it takes to access memory, many nanoseconds. You may be wondering if caches like the translation look aside buffer are so great. Why don't we just make bigger caches and keep all of our data in them? Unfortunately, this is where we run into more fundamental laws, like those of physics. If you want a fast cache, it has to be small, as issues like the speed of light and other physical constraints become relevant. Any large cache by definition is slow, and thus defeat the purpose. thus we are struck with small, fast case. The question that remains is how to best use them to improve performance. Right. So what happens if the case is run out of memory, something like that? What is the cleanup mechanism or the policy, I guess? Policy to remove the unused memory translation in translation asset buffer. Maybe that's the question. Oh, okay. I'm not sure if replacement policy. Okay, maybe we will get the answer in this section. The replacement policy. Okay. Alright. I guess let's continue this section 19.3, who handles the TLP miss, in the next session. So that's it for now. Thank you for watching and see you next time. Bye bye.